Carbon dioxide is a serious issue. Growth rates of CO2 have tripled since the 60s, with the global average concentration surged to 3.5 ppm, the largest increase since modern measurements began in 1957. The continuous emissions of CO2, surging wildfires, and the decrease of effective carbon sinks is a vicious climate cycle. If we don't break free from this cycle, this could be the end of life as we know it. Okay, maybe that's a little dramatic, but let's be realistic here. Earth is in a dire situation right now. There has to be something we can do. And by we, I mean us. Meet the team. We were on a mission to design and build an efficient and inexpensive carbon removal device. But we wanted something different. Something that could stand out in a crowd of carbon removal projects. Something drifty.
What? Drifty? Professor! Check this out!
Can you see these tiny specks moving slowly?
Hello!
These are tiny zooplankton. Now, don't underestimate these little guys. They play an incredible role in removing CO2 from the atmosphere. Don't believe me? Let me show you. In the marine world, zooplankton act as a biological carbon pump by absorbing CO2 from the atmosphere and sequestering it in organic matter. This matter, whether fecal pellets, mucus feeding webs, molts, or carcasses, sink into the depths of the ocean, where it can be stored for a long period of time. So I thought to myself, could this biological carbon pump be achieved on a smaller scale? Zooplankton and phytoplankton, algae which is their food source and what absorbs CO2, require time to grow. So for 7 weeks, we raised 3 species including the North Pacific krill, brine shrimp and rotifers, with Anu feeding them phytoplankton twice a week and June replenishing our mini aquarium with seawater. So our initial design looked like this: growing zooplankton and phytoplankton in a container with a bubble pump, some light source, inside another box pumped with CO2. And this was our final result. An alteration included the pump being taped on the lid inside the box, with rocks securing the silicon hose below, with a small enough gap for CO2 to be pumped into 15 liters of seawater, 30 milliliters of zooplankton, and 60 milliliters of phytoplankton. I should also mention this container here, filled with limestone and seawater, but that's for June to talk about.
On this part, we have ocean alkalinity as the side project. In the beginning, we have the idea to combine the 2 planes together, which is we want to put zooplankton and the ocean alkalinity together and test them out in the same box. But at the end, we found out it may not work quite well. And I will talk about the reason later on. So the idea of ocean alkalinity is to mine the mineral that can make the water pH increase, such as silicate or limestone, and send them into the ocean. Therefore, the pH will increase and you will allow more carbon dioxide to be stored in the ocean base. The pH percentage of the seawater we use is about 8.3, and we're trying to increase the pH to around 9.5. That it's the safe range for the sea creatures, and we want to see how it goes if we combine them together. So in this project, we are using limestone powder. It could better integration into the salt water than limestone. We put zooplankton together into the salt water in the box and see why it's go. So we totally put 1 grams of limestone in 10 liters water. and we want to find out what will happen. And as a result, we see all the zooplanktons, they all die. Maybe because of the pH change. I'll say that later on. The reason why those zooplankton die. So this video it record for the final test, and we can see the increase of the pH from the store water. It increased from 8.3 up to 10.1, and we only put 5 grams of limestone in 10 liter salt water. And this increase, the zooplankton is not able to survive. And before this test, we tried to put zooplankton and limestone together. We put less amount of limestone, like 1 grams or even less. We try to expect them survive together. And from the result, we found out even a small change of the pH, it can create a big effect to the zooplankton. So we think better we just separate them and do separately the test. So once we notice we can't put zooplankton with limestone together, so we separate them into 2 different boxes and we do 2 tests. And from the result, we can see because only we put a decent of small amount of limestone, the effect not quite good, the result. And I know we covered the result part.
So, what results did our experiments give us? As we had 2 different tests, one with zooplanktons and one with limestone, we measured how these will absorb CO2 over 1 hour time. Each container started with different CO2 levels. The zooplankton started at the highest, at around 48%, while the limestone started at about 35%. Now look at that. You can actually see the CO2 levels are going down over 1 hour time. Zooplanktons drop really fast, from 48% down to about 23% by the end of the hour. And the limestone dropped a little, from 35 to around 31%. So what does this mean? The zooplanktons absorb more CO2, showing they're really effective at absorbing the CO2 levels. The limestones also help, but not as much. It caused only a small decrease compared to the zooplanktons. So, from our results, we found that zooplanktons work the best in reducing CO2 levels over time. Unlike limestone, which changed the pH too much, zooplanktons remove CO2 in a natural and balanced way. They're living organisms, so they don't create any waste or chemical pollution. They just use CO2 as part of their normal biological process. This makes them a really sustainable solution. They can keep absorbing and storing carbon while supporting marine food webs at the same time. Our experiments showed that even tiny organisms can make a big difference when it's come to tracking climate change. So maybe the answer isn't always just high tech. Sometimes it's already floating in the ocean.